Hello, everybody. First of all, I'm glad to stay here today, my first time in the community, see a lot of people that we usually interact with here. And today we're going to present the status of the Virtual Kernel Mode-Setting, or just VKMS. So basically, I will start to introduce ourselves, since we are new here.
So I'm Haneen. I'm from Saudi Arabia. First-year PhD student at Columbia University. I worked on VKMS as part of my internship with Outreachy this summer.
So my name is Rodrigo Siqueira. I'm from Brazil. I am a software engineer, and I'm close to finish my master's degree. And I get into the VKMS project thanks to the Google Summer of Code project. As a result of our internship, we had some mentors, some great mentors that help us during all the summer, which is Daniel Vetter, Gustavo Pandovan, Shampoo, and all the DR Devel communities, since everybody here provides some feedback to us, and thanks a lot for all the help during the summer. So before I start to talk about the VKMS, I think it's important to make a brief recap about the kernel mode-setting. The basic idea behind the kernel mode setting, it is a mode setting operation, which is, in a few words, it's responsible for set the resolution, the color depth, and the refresh rate in the graphics stack. So, and all of these things works on the kernel side, and there is a subsystem named the Direct Rendering Management, or just DRM, that do all of the hard work on here and do actually much more than this. And DRM, it's important for allow us to use many graphic applications allow us to use the same GPU for provided processing for many user process. So as a result, maybe we can think, why do we need something like a virtual kernel mode-setting? And there is some reasons. There is a lot actually, but there is two main reasons. First of all, we can use VKMS to increase the DRM test coverage, which means that we can run some tests without the requirement or real GPU that make some verification that DRM works well, for example. And we can make something more interesting with that, like we can create like a continuous integration environment with VKMS. We can create something like start a virtual machine that use VKMS and then run some tests in this virtual machine. So it's good for continuous integration. Additionally, it can be a useful tool for people that work with graphic stacks, such as developing graphic environment, such as Wayland or X.Org. They can use this as a tool for testing compositors and things like that. So with this idea in mind, it's important to highlight that me and Haneen are a little bit new in the DRM subsystem, so we are basically newcomers, and start to develop such a driver from scratch, it was a little bit challenging. But we are lucky, because we had some development cycle which is based on test-driven development. And we just have it because of a set of tests implemented by the Intel team. The name is Intel GPU Testing, or just IGT. And in this set of tests, there is a lot of basic checks, like how can make a page flip, how can use Vblank or CRC, these kind of things. And we used this to guide us during our development. We basically take the IGT project, we patched it to accepted VKMS, and then when we changed the IGT, we started to run some specific tests on top of VKMS. As a result, we can see what kind of feature we have to implement it on VKMS. So basically, we watch the IGT test fail. When it fails, we write some codes that make the test pass. And it's important to highlight that we have two situations when we write the code to make the test pass. First of all, the test can break. And if it breaks, it means that we need to implement something that it's required for that test. It not even fail. And after we implemented it, probably the test will fail, which means that there is something wrong in the way that we implemented it. With this idea in mind, we worked a lot for make some test pass, And when it passes, we start to improve the code. Basically, we send a patch for the community, and we received a lot of feedback and keep improving it until it reached the DRM MISC branch. So when it finished, we finally get our patch accepted. We started again the process, run again the IGT test, a different one, and start to implement it. This is our workflow, and we used it from the beginning until now, and we probably will keep using it. So with these ideas in mind, it's important we can now start to look inside of VKMS, all the features that we have implemented during the summer, and I want to start by providing some basic overview of what we have. First of all, we need some basic setup on the VKMS to make the tests run without break. So because of this, VKMS provide frame buffers. We provided additionally 2 planes, a primary and a cursor planes. We provided 1 single CRTC. It's, for now, we just have 1, but we can improve it to have more. We have 1 virtual encoder, and we have 1 virtual connector. All of these basic features are required to make the test pass actually run. And the picture does not show, but we also have some functions to handle the Gen memory. Gen is handled there. So now we can start to talk about some more interesting features that VKMS provided. One of them, it is a page flip and Vblank. The page flip, the basic idea behind of page flip, it is illustrated on that picture. First of all, we have 1 back buffer and we have a primary buffer. The back buffer are the GPU pointed to the back buffer, which means that the GPU write on there the next image, for example. And we have the primary buffer that it's pointed by the screen. And the screen always pointed to the primary buffer. After a specific amount of time, something happened. DRM start to make some operation named flip, which basically changed the primary buffer and the back buffer. And now the primary buffer, the screen points to the primary buffer, which was written by the GPU, and GPU start to produce a new image. This is an oversimplification of the process of page flip, but this is what we have to, this is the kind of features that we need in VKMS. And I talked about some amount of time to make this change. And this amount of time receive a special name, which is Vblank, basically. And the Vblank, it's a signal produced at the end of a specific period. And usually, GPU has a special hardware that produces this signal. It means that in a real GPU, this signal is really precise. And we can guarantee that the interrupts will always occur in the expected way. However, VKMS, it's not a real hardware. It's a virtual hardware. It means that we have to fake it in some way. And the way that we decide to fake it, it is by using HR timers. So to better understand how it works, think about time as a timeline, as can be seen in the picture. And we can divide these times in multiple slices. These slices are, for example, the period. For example, suppose 6 Hz, which is around 16.6666 milliseconds, and we have all of these slices. We divide the time in all of these slices. So we expect that at the end of each period, we start a signal. We send a signal to someone or some function, doesn't matter here, make some specific operation. And if we simulate it on a software, as we do, we have some problems because we does not have one dedicated hardware that will produce this interrupt. It means that we are doing it on a software layer, and then we have some delays associated with the period. As a result, the period sometimes is a little bit larger than we expected. And then we have to fix it. Otherwise, we will lost the period sequence. And this is not a good idea because we can break the user space if we make some mix on the period, on the time period. Fortunately, HR Timer API, it's a really nice API that already do it for us. If we have some delay, for example, HR Time detect it and then try to fix to keep the period constantly. This is really good for, in our case of the VKMS, because we can always keep the period constant. So, in a nutshell, for implemented this feature in a VKMS, we have just a few functions. First of all, we start at a VKMS enable Vblank, which basically it's a function that it's called at the module load, and it basically makes some basic setups on HR timers, such as the period, and most importantly, which is the callback that have to be called every time that the period is finished. In our case, it is the VKMS Vblank simulated. Basically, this function is invoked every end of the period, and it calls DRM CRTC handle Vblank that basically updates the Vblank count and also handles some pending signals. And after that, this function basically schedules another period with the HR timer. We have to do some trick here because we are simulated something which does not have a fixed period. Sometimes we have to fix the time, as I told you before, with HR timer, and we have to say the correct information for the user space. And because of this, we had to wrapper the function getVblank timestamp for our function, and we return for the user space the timestamp of the last HR time finished. So we have to do it to make it work. And also, we have some extra feature related to this. It's basically run VKMS without Vblank, but it's not landed yet because we have to make some fix. It's a patch. But basically, the idea is enable VKMS to run without Vblank, because this can be useful for testing compositors, for example. So basically, it's a modular option that you can say that you don't want Vblank on a VKMS, and then you can just make the page flip. However, we still have to send a signal for the user space that we finished some operation, the Vblank. So we faked it by using the function DRM send Vblank event that basically make the simulation of Vblank signal. This approach is similar to the one implemented by the bot module, and it's worked pretty well on the test. At the end, we had some basic tests. For example, maybe it's a little bit dark here, but basically it's an example of the execution of basic page flip, which makes some tests for a lot of tests actually to check if the page flip works as expected. So as a result, the option with Vblank that I'm showing here works well. It's passing all of the tests. The option without Vblank also works well, but I still have to fix some of the paths that I sent to IGT in order to get it landed. And finally, we can see some tests that send the timestamp to the user space, and we check if it's correct or not based on the time sent. Again, everything works well, and this is the kind of test that we skip if we are not using the Vblank implementation.
So next, my main task on VKMS was to add CRC API support. Basically, CRC is a checksum. It's an error-detecting code that gets attached to a data frame so that the receiving end can detect and can check the data integrity. And in DRM, CRC API provides user space CRC information of the final frame shown on the display. So basically, why is it important? Why is CRC important? Because it's used for testing. Like the IGT test uses CRC to verify if the correct images are being displayed on the screen. So as a first step to get VKMS going as a driver, useful for validating against IGT test is to add CRC support. My main task was to pass these two tests, the CRC basic and cursor CRC. The tests work as follow. Basically, we push a frame buffer update and then start collecting CRCs. If you want n CRCs, we wait for n Vblanks, and then once we collect the CRCs, we try to verify if they're equal to what we expected and if they're all equal to each other. To add CRC API to a DRM driver is quite trivial. You just need to implement these two functions, verify CRC source and set CRC source. Once these functions are set, the debug file system files are going to be set automatically with two files, control file and data file. And then the CRC samples, which are usually provided by the hardware, need to be captured in the driver by calling add CRC entry. On the user space side, the user can control the generation of the CRCs by writing to the control file, and then they can capture, once the CRC generation is enabled, they can capture the CRCs by reading from the data file. So as I mentioned, CRC entries are usually provided by the hardware, in which the driver would pull for every frame. But since VKMS is a virtual driver, we needed a way first to access the frame buffer and then compute a unique CRC value per frame. So the general idea would be we would go over the set of pixels in the visible area of the screen and then clear the alpha channel, because currently we support XRGB, which ignores the alpha channel, and then compute CRC. We've used CRC32 as the function to compute the CRC. It didn't matter if the system is Little Indian or not, as long as we get a unique CRC value per frame. So the next challenge for me was to understand how the plane properties and frame buffer properties map to the actual displayed screen. So how to iterate over all the set of pixels. So once I figured how the mapping worked, basically we'd go over the set of pixels line by line, and then for each set of pixels, we go through each pixel and clear the alpha channel and then compute CRC. So this is for one plane, primer plane. What if we have two planes? Then we would need to first blend the two planes together and then compute the CRC on the resulted frame buffer. So now that we have a CRC value, we're ready to report it to the user space. I thought this would be trivial, but apparently it was the most challenging part throughout the internship, because we had to solve the synchronization issues. Mainly we have two tasks that are working on the same data. The atomic commit would update the CRC data and then send the Vblank after page flip event. Independently of that, the Vblank handler would fire every Vblank interval, and then it would handle the Vblank and then read CRC data to compute the CRC value. So ideally, we want to compute and report a CRC value that is associated with the page flip event. Well, sure, we would use some kind of locking, but the question was where and for how long. So if we get closer, look at both tasks, we would notice that the CRC data get updated from the plane atomic update. And then after the atomic commit, at the end of the atomic commit, this Vblank gets sent. On the Vblank handler, we first handle the Vblank and then issue a queue, a work strict that would then compute the CRC. So we wanted to make sure that the CRC computations would have a consistent view on the frame buffer, even during a frame buffer update. So the current approach, basically, we lock across the atomic commit. So we lock across the atomic commit to prevent sending the Vblank handler before we update the CRC data. And then the Vblank handler, we don't handle Vblanks while the lock is held. And by that, like, we have addressed that issue. But there were other issues as well. Like, what if the CRC worker falls behind while computing the CRCs? Like, what if the next atomic update happened, but the CRC worker hadn't finished its work? Also, what if there were no atomic update, but we still have to generate one Vblank per frame? So after overcoming these challenges, we've managed to pass these set of tests. And thus, I've concluded my internship period, and Rodrigo will conclude the presentation.
So, in conclusion, it's important to highlight that VKMS is a work-in-progress project. We still have a lot of issues to handle related to the KMS flip or the CRC part, but we'll still work on it. And we have some, in our near future, we want to make Wayland run on top of VKMS. And also we can have the opportunity to implement many other features in the VKMS. And finally, for feature reward, probably I will get extra 5 months work on VKMS and in the DRM community due to a scholarship provided by Brazilian government to work on it. So I hope to have a discussion with many of you guys here for find some features for implemented. And we finish here. Thanks for all the help and all the attention. And we are open for questions.
Any question? Any question? Okay.
So, what's the difference between implementing the cursor plane and implementing just generic overlay planes?
Sorry, I didn't listen.
What's the difference between implementing the cursor plane and just generic overlay planes?
Did you understand?
Overlay plans?
Yeah, like why not enable overlay planes in addition to cursor plane?
Yeah, I think we can, like, the same workflow would be implemented, but we still doesn't, like, we don't support overlay planes yet. So yeah, we just have like primary and cursor planes so far.
I was just going to say there actually is a couple of differences, mainly some of the legacy ioctl APIs that you use for cursor planes are a little bizarre. They're not really rate limited in the same way that overlay planes are, so that might be a big difference between the two.
Again, yes, like, we still didn't, like, get to overlay planes, so I honestly don't have an idea of how they work yet.
Hi. So first, thank you for this awesome project, because we were looking in Quinn to extend our auto tests for DRM backend as well, and this comes in handy directly. one question for, you had one bullet point where it said like you want to do Wayland on top, I think one slide back or something. What do you mean by that?
Oh, sorry. Basically, what I mean is that I want to have some compositor running using VKMS. I probably will have some talk with people that work with Wayland today and tomorrow to get more ideas how can I do it and the correct way to do it and actually the right way to express myself about it.
Any other question?
What are your plans for implementing write-back connectors? Do you have any yet, or?
Write-back connectors? Write-back connectors.
Yeah. We actually did not think about it yet, but maybe we can discuss later with you to get some ideas.
Yeah.
I guess this is all. Big applause to them. Come on. Thank you very much.